ce cours en anglais, mais vous avez le droit de me parler en français. Hein, ça va encore et je peux vous répondre dans la langue que vous voulez, hein, si c'est l'anglais ou le français. So this is the course LINFO2345. So, so this course is going to teach you all about distributed systems, distributed algorithms. So you can start the video. I am Peter Van Roy. I'm going to teach the course. The teaching assistant is Mathieu Picagno. Who is coming all the way from Bordeaux to join us as researcher. Unfortunately, he's not here today, but he will be here starting tomorrow. So there will be a lecture every Tuesday from 16:15 to 18:15 in this room, Studio 5. And there will sometimes be labs, not every week. Also, same hour in bar 20. So the labs will not be every week. So there will be no lab next week. The labs have two purposes. One is prepare for the midterm. So there will be some lab exercise sessions for that. And the second one is prepare for the project. The course project. Okay, so the first part of that will be learning Erlang, which is a really nice language for building robust distributed systems. If you do not know Erlang, if you only know Java, then too bad for you, because Erlang is really nice, but we're going to teach you that. It's very easy language, actually, to learn. And we'll be using that for the project. Okay. So let me explain a little bit how we're going to organize the course. So there will be a project in the second half of the semester. This project is mandatory. It's worth 5 points on your final grade out of 20. And normally you have enough time to do a very nice project. So hopefully everybody will already get almost 5 points. So that means you're very happy you almost succeeded in the course already. Okay. It will be done in groups of 2 people. Binôme. Groups of 2. And the points will be valid for the whole year. For both sessions. But only for 1 year, so not for the next year. But if you do really well on the project and you still manage to fail the course, strange, but sometimes happens. If you do really well on the project and you ask me very nicely, I can usually make it count for the next year. But it will have to be at least 4 out of 5, okay, on the project. But that should be possible. There will be a midterm. Written midterm, which is worth 5 points, and an exam, which is worth 15 points, but 5 plus 10. So what that means is if you do really well on the midterm, then you do not have to do this part of the exam. Because the midterm will dispense you of 1/3 of the final exam. If you do very well on it, you really don't have to do this. But even if you do badly on this, in any case, I'm going to take the maximum of these 2 points. And so then you have 10. That means if you do well on the midterm and well on the project, then you already succeed the course. It's nice, huh? So this, if you do well here, then you actually have to do less work. And so this dispenses you from that part at the end. So this approach works really well. So it encourages you to work more during the year, and also it makes less stress at the end, okay? So the exam is not supposed to be a championship of stress management. So I always try to de-stress for the exam. Okay? So what is the course material? So the course material will be on the slides. So the slides will be the whole course material. However, these slides are based on, most of them, for the first half, is based on this really nice book by Rashid Garawi and Luis Rodriguez on Introduction to Reliable Distributed Programming. So this book is really one of the first books which really explains distributed systems in a nice way. Okay, and it's still probably the best one. There's a second edition of this one which adds secure, so it's reliable and secure distributed programming. So I'm not going to talk this course a lot about security, because that's a big subject, and that would be, there's a whole course just on security. Yeah? But this second edition is a superset of the first one. So you can get the second edition also, and this one will explain things like Byzantine algorithms and stuff like that. So these books are really nice. They contain a lot of material, a lot of explanations, a lot of code, pseudocode, which is nice and simple for the complicated algorithms that we're doing. Okay. So another point is I will try to record every course in a video, but there's no guarantee. It depends on the technical. I hope nothing wrong happens with the camera. So the recording is working well, right?
Yes.
Okay. So I will try to do that and make it available to everyone. But still, I hope you come. I hope you are so disgusted with online things that you will come anyway to see the lectures in person. Okay. Okay, so that's all about the introduction. What else should I say? Okay, I'll say a little bit more about the project before going into. So the project will be done using a language called Erlang. So Erlang is actually very old. It's as old as Java. It's old like Java. Well, it comes from around 1988. It was developed in Sweden by Ericsson, but actually by a small group in Ericsson, led by a guy named Joe Armstrong. And Ericsson almost killed this project several times. Ericsson wanted to make telecommunications. So maybe you have mobile phones that are by Ericsson. They also have routers and switches. Ericsson is a very big company doing that. They do it very well. And in the 1980s, they wanted to make the end-all best operating system for telecommunications. So they wanted to do it in C++. I have no idea why they picked C++ for telecommunications. So they hired 1,000 programmers, and basically after a few years, the whole thing was a complete failure. And you can look at it, it's a famous failure. There's a Wikipedia page on explaining how this whole thing failed. Okay? I know some of the people, so I'm not going to mention their names, because this is being recorded and I want to stay friends with them. Many of them are still alive, okay? So luckily, they had the Erlang project, which was very successful. There was the Erlang project, so it's actually, socially, it's interesting to give you some explanation. So it was led technically by Joe Armstrong, but it had a protector called Bjarne Dekker. So Joe was the technical head, and Bjarne Dekker was the white knight, was the executive who defended this project. Okay, if you go into a company, it's not enough to be technically very good. You need somebody to defend you. So Bjarne did that, and because of that, this project survived, and even now it's being used in many different telecom systems. So many cloud systems that you use are actually written in Erlang. Usually the companies don't advertise, but many big companies today are using Erlang for their software. So I don't know all of them. One of them is a company called Bet360, which does online betting. I don't recommend you do online betting, but their stuff is written in Erlang, okay, using the database called RIAC, which is a big cloud database written in Erlang. So this system is really good industrial system, but it's also very easy to use. It's very easy to use system, so it's great even for projects. So you can very easily start using this system, okay? So, and the notation, the code, is similar style to the pseudocode of the course. Okay, it has a very nice way of building distributed systems. So basically you have concurrent agents in a layers that send each other messages, okay? So it's a very different way of writing programs than in Java. You have many concurrent agents who do not share any data, no sharing, that's a basic principle, and they send each other messages, and they're all running concurrently. So an Erlang program, that's how it works. Okay, it's not one big program that runs like Java, it's many small programs that are separately running and sending each other messages. And there can be hundreds or thousands of these small programs. This is the perfect system for building distributed applications, robust, fault-tolerant distributed applications. Okay, so that's the one we're going to use for the project, and I hope you like it and that you will see how nice it is to use. So let me say a little bit about the course, what we're going to see in this course, and then I'll start by starting some technical teaser. After that, I'll give you some slides, and I'll give you kind of a teaser on some of the concepts we're going to learn. Okay? So this course is going to talk about distributed systems. So a distributed system is a bunch of computing nodes sending messages to each other. This course is going to be very rigorous. I'm going to give a number of mathematical definitions, foundational. So it actually needs some mathematical maturity. Some of the concepts are very powerful. It's all very powerful. I'm going to give you the most powerful concepts I know, okay? So, but to really understand them, you have to think a little bit. So one of the purposes of this course is to get you to feel that power, okay? The intuition of that. So I believe very strongly that to understand mathematics, you need intuition, okay? So that's one reason why I strongly recommend that you attend the course. That's also why I'm making videos, so you can look at it. The intuition is not always on the slides, but I will tell you the intuition. And if you have questions about certain subtleties, you can ask any kind of question about it, and I will try to answer, okay? So these concepts are very strong, so you can attack them. You can say, that's totally bogus, for example, and tell me why you think it's bogus. And then we can discuss, and then you will understand even better the concepts, okay? So that's very important, the intuition. And you'll see it today when I start giving you the little teaser. So today, I'm not going to plunge into too many very difficult concepts, but we're going to start with some very interesting kind of puzzles and problems. I want to get you thinking a little bit, okay? So the course is actually in two parts. So the first part is going to be about small distributed systems. Small systems. What do I mean by small? Maximum, let's say 20 nodes, a small number of nodes talking to each other. Okay? And usually they are pretty static. So the number of nodes does not change very much. So these can be small systems like simple client server or simple peer-to-peer, or even simple databases where you have a couple of replicas talking to each other. So many applications are like this. Okay? But then you have another kind of system, which I call the large systems. So the number of nodes can be extremely large in such a system, 1,000 to millions of nodes or more. They are almost always dynamic, which means the number of nodes is always changing, because that means nodes can be failing, or new nodes can be arriving or leaving the system. You can have groups. So these can be like peer-to-peer systems or social networks. So companies like Twitter and Facebook and Google, internally, they have a lot of these, okay? A system that has to support the message passing, for example, done by Twitter, it has thousands of nodes internally, okay? Because of the huge scale, the number of users, the geographic scale. And they are almost always dynamic. That's pretty logical, actually, yeah? If you have 1 million nodes, it's very hard to make them all not fail, okay? If you have 1 million nodes, there's always going to be a node in there that's failing, or new nodes are coming. The number is not exactly fixed. It's even very hard to find out how many there are. So one of the algorithms we're going to see in this course is an algorithm whose purpose is to find out how many nodes there are in the system, okay? The network's the size of the system. Okay, so this is the second part. So the first part of the course is mostly based on this book, but the second part will be very varied, okay? It will be, there's so many things I could talk about here. I'm going to talk about peer-to-peer systems. I'm going to talk about overlay networks. Maybe, we'll see, yeah? I'll talk about gossip algorithms. Gossip algorithms are actually extremely powerful, and the idea is very simple. It's gossip, bouche à oreille. So the nodes, each node has a small number of neighbors. That's it. And the neighbors have their own neighbors, and so on. So nobody knows how big the system is. And if you want to tell something, the node will tell the neighbor. And the neighbors will tell their neighbors, and so on. And nodes can fail, they can get new neighbors, and so on. And you could actually do very powerful things. And it's even quite efficient using gossip algorithms. So these are actually used a lot. Peer-to-peer overlay are also used a lot. So for example, a system like Skype, which has to do video or voice communications dynamically between millions of possible users. You can see the infrastructure is complicated, right? How can it know when I want to connect to somebody? It has to find the guy, make the connection efficient, and so on. So Skype is using an overlay network. It's also using gossip algorithms because it tries to be decentralized, which means there's not one node controlling everything, okay? The control is spread over many nodes so that it never fails, huh? Right? Skype never fails, right? Well, it supposedly never fails, okay, or not so much. But if there was one node controlling everything, if that node was down, everything would go down. But it's not like that, okay? So what other kinds of things? Content distribution, things like Netflix, okay? How does it handle video on demand with millions of users in an efficient way? Okay, so and then there's other kinds of stuff we'll see. So I can actually propose things, and we can vote on what you think is the most interesting thing to talk about. Okay? Okay, so that's basically how the course is going to be organized on the slide. So I'm going to give you a little teaser now. But first, let me just remind you something. So there's a Moodle for the course. So please register yourself on the Moodle. There's also a Teams team for the course. Please register yourself on that. And of course, there's the UCL enrollment inscription. Please enroll yourself, okay? So there's 3 kinds of enrollment, yeah?
Are the updated slides on the Moodle?
Yeah, I put these slides. The slides will always be in the Moodle. I will put the slides in the Moodle. Right now, there's only these, the first lecture, but I will put the other ones on the Moodle. Okay, so you will find them all on the Moodle. So don't forget to register yourself. All the information comes on the Moodle. Okay, so then we can start. So, first of all, what is a distributed system? And this guy, do you recognize who that is? He's probably the one most famous person in distributed systems theory, algorithms. His algorithms are running on systems all over the world. No, you don't recognize the guy? He's Leslie Lamport, and he says, this is his definition of a distributed system. Sorry, his name should appear, but it's Leslie Lamport, and he says, distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Something else fails, and your system doesn't work. Okay? I see there's a problem with that. So it's Leslie Lamport. Okay? So more technically, for this course, a distributed system is a set of computing nodes connected by a network which appears to its users as a single system. Okay? Coherent, providing a single functionality. And in this course, we're going to study this kind of system in a fundamental way, okay, with concepts, models, foundations. We'll know how to specify them, how to understand them. And you'll see that it's actually pretty subtle. It's probably the hardest kind of system to write good applications for, and I'll explain for you why. So, why are distributed systems something that we study? Well, they seem to be important. There's some small thing in the world called internet, okay, which is a distributed system. The web running on top is a distributed system. Small devices, mobile phones are connected to these infrastructures. Even now, we've Internet of Things, sensors and so on, they're all connected together. So there's extremely many systems connected together, and even in a single node is now multi-core, okay? Multi-core systems with 4 core, 6, 8, 10, 12, whatever, so it's already a distributed system. Okay? So we want really to understand this. Reliability, scalability, the system is very big. The inherent distribution. So these systems are inherently spread out. You cannot put them on one node. Okay? So here's an example of one. So this is a photograph of one hallway in one of these big Google data centers, where they usually have 100,000 or so nodes. In Charleroi, there's a Google data center. Have you ever seen this one from the outside? When you go to there is a very metal barbed wire fence around, and even far from the building, so they can see whenever the terrorists come, okay? When you want to drive in, they have things under the road, which if you back up, it basically destroys your tires, okay? So if they want you to stop, and they have like metal barrier that can stop. So this thing is very important somehow. They are protecting it. It's almost like military installation, okay? So here's another one. This is an old one, but a very nice one. So this is a system called PASS. So this was in the space shuttle. Do you remember the space shuttle was a very nice thing, reusable for going into space. So the computer in here should not fail. So they actually have 4 nodes doing the computation and making a vote. They're doing the identical computation and making a vote. So if 3 of them agree, and 1 of them has crashed, then they can do things. Okay? If all 4 agree, it's very nice. You know, in practice, if 3 of them agree and 1 of them has failed, you think everything's fine, right? Actually, no. Actually, the humans start panicking. Because if 1 of them fails, maybe the second one will fail too. Who knows why it failed, you know? Okay. So this is actually a very delicate kind of system. Okay. So this course is going to be fairly mathematical, but also programming. And it's very challenging to build these systems. So why is it challenging? It's the hardest kinds of programs to get correct. Okay? And the reason, there's basically a few reasons. One of them is that you have partial failures. So when you write normally a program on running on one machine, it crashes, right? Or it doesn't crash. It's a total failure, okay? Or it just runs. But in the distributed systems, you have many nodes talking to each other, so you can have part of the system failing. But the rest of the system has to keep running, okay? It's not because part of it fails that the rest stops. In the joke of Leslie Lamport, if one of the nodes fails, the whole thing fails. No, you don't want that, okay? The rest of the system has to keep running. And this happens all the time. It's very normal, okay? When you write a program in Java or Python, you don't want it to crash, okay? It's not normal to crash. But in the distributed systems, failure is a normal thing. And this is intuitively hard for people to understand, okay? So a system like Erlang is designed from the viewpoint that things are going to fail, okay? So Erlang says, we know things are going to fail. What do we do to make it work? Okay, so failure is normal, and partial failure. So network, where the messages are dropped, or even if I have 10 nodes, they can split, so that these 5 can no longer talk to these 5. Maybe there's like one router connecting this group of 5 to this group. This is called, in a big system, this is sometimes called split brain problem. Okay, it's called a partition. So one part of the system thinks that the other part has failed, and the other part thinks that the first part failed. How do you handle this? So this kind of thing, you can imagine, is not easy to handle, okay? In this course, we're going to look exactly at the hard stuff, okay? In this course, we're going to look at the tough problems and what can you really do in that case. Okay, so it's not just node failure, but also network failure, and it can happen anytime. Of course, this is on top of the usual difficulty, which is concurrency. Yeah? So you have normally already some experience with concurrent programs, right? You've written some concurrent programs where the nodes are executing at the same time. They can talk to each other, for example, with messages. So this is already hard, to get it correct. If you add partial failure to this, it makes it even much harder. So how do you write even code for this kind of a system? How do I write code? So that it's easy and I can be sure it's correct? That's very important. What kind of a programming language is going to do this? So we're going to introduce in this course a really nice, simple, powerful pseudocode. Okay, there's no language that exists that is actually the perfect language. The closest one is probably Erlang. But in this book, they introduce this really nice pseudocode, which lets you build these systems, and you build them as layers. Which means you build a first layer, for example, that does a broadcast. And then you have a second layer that makes it reliable, and a third layer that adds things like causality to it to make it better, or to make it atomic, or other things. And each layer is doing one thing. If you write code with all of that stuff together in one big program, it's a total mess and nobody can understand or prove it, okay? It's just too complicated. This is really the most complicated, probably the most complicated code, conceptually complicated, you're going to see in your courses. Maybe later, when you go work, you see worse stuff. It's probably here. I'm trying to make it simple. So this book, which came out in 2007, was actually the first one that made this code fairly simple. That you can actually understand each layer and you can prove why it's going to work. Even though it's concurrent and partial failure, you can actually be confident that it's working, okay? And you can see, you can't just write code. You need very good concepts there. Huh? So that's what we're going to do in this course. And I'll show you a little bit of that today, but in the next couple of weeks, we're going to see the pseudocode. And this is a really important model for writing this complicated code, okay? So there's actually, one thing I want to say now, there's a difference between what people call parallel computing and what people call distributed computing, okay? When scientific computing, for example, which is what they do, for example, at CERN, when they want to compute the trajectories of subatomic particles and so on, it's very large scale, but usually there's no failure, okay? In parallel computing, you have what they call a grid system, which might have 10,000 or 100,000 nodes. And they actually have a grid here at UCL, and many places have grids. So these nodes will not fail, okay? Or almost never fail. So parallel computing is only when you need speed, okay? So there's a big difference between these two areas, parallel and distributed computing. Parallel, basically you will have no failures. And why do you do things in parallel? But to make it go faster, okay? Because you want speed. In distributed computing, you will have many failures, and the purpose is not speed. The purpose is the system is separated. There are geographical separation. I am here, and I'm talking to a guy in Japan, and we're both talking to a guy in California. It's geographically separated, and it's forced on you, okay? And because we're separated, things can fail. In such a big system, when I'm talking to Japan, there's many ways the communication can fail, okay? So these systems are also called loosely coupled systems. So this is a fundamental distinction, and these are called tightly coupled systems. In these systems, there is a fast, very reliable network connecting the nodes, and there's no failures. And the purpose is speed, because they want to do a quantum chromodynamic computation, and they need to go 10,000 times faster than this little guy, okay? Because it's huge computation. Or weather prediction. The European weather model is extremely good. And I can make a small plug for Europe here. It's even better than the American model. So when they have hurricanes coming into Louisiana or Florida, we give better predictions than the Americans do for their own things. And it's using a very huge parallel computing system, a grid with a huge number of cores. So the purpose is not distribution, it's speed up, okay? So this is a fundamental distinction, parallel versus distributed, and in this whole area where you have multiple nodes talking to each other, these two groups are thinking in very different ways, okay? So distributed is, for example, internet is a distributed system because it's spread over the earth, whereas the parallel, these are what usually are called grid architectures. The purpose is speed, whereas the purpose of the internet is not speed, it's connecting people, okay? The purpose of the internet is connecting people and letting them work together. Maybe you want speed, but it's not the first reason. You want to connect them because they're separated. And because they're separated, the connections are very loose. The people are far away. So this is a kind of loosely coupled system, and these are tightly coupled. Okay? So this is fundamental. In this course, we're going to talk about distributed systems. Okay? If you want to talk about parallel computing, you can go to another course. But parallel systems are actually simpler than distributed systems. There's no partial failures, and the networks are very tight, and the latency is very low, very high bandwidth. So they don't have this partial failure that distributed systems have, okay? So we're attacking the hardest problem of infrastructure, the hardest kind of infrastructure to do computing, okay? That is distributed computing with partial failure and concurrency. Okay, so now I want to give you some intuition. I'm telling you it's very hard, and it is very hard. So how do we present it? Well, we will try to present it in the simplest possible way. So you cannot get around the difficulties, okay? It's very hard. But if you present it in the right way, it becomes understandable. We can actually start to understand it, even though it's complex. So when people are researching these systems, they find that in this kind of system, there's certain kinds of problems are always reappearing. They're like some very important problems that are always coming back. So it's like you're always doing the same kind of problems, certain problems which are called core problems. So I'm going to give you some intuition on that. So the most important problems in a distributed system are the core problems. And I'll give you some example of that. So the first core problem, probably the most important one, is called agreement or consensus. So the idea is, how do you get nodes to agree? Okay, that's reasonable, right? If you have a group of people, how do you get them to agree on something? Well, in a system, it's like that. So let me give you a kind of puzzle. This is actually a famous problem. This famous problem, it was first used by Leslie Lamport to explain consensus. This is called the two generals problem, where you can have the n generals, but we'll just do two, which is good enough. So you have two generals, each one has an army on the field, okay, with hills and so on. But they're kind of far away, but they can send messengers to each other, but they're like kilometers away. And there's a center, another place where there's like an enemy. So these two generals, they don't have radio or anything. This is Byzantine, Middle Ages, okay? They cannot talk to each other by radio, or it's jammed or whatever. They have to send messages. So they have to agree to attack at the same time. If they attack at the same time, then they have enough power to win. Okay? And it's the only way they win is that they attack simultaneously, at the same time. So they have to agree. But how do they agree? Well, the only way they can talk to each other is by sending messengers. So one of the generals gives a message to the messenger. The messenger runs on the field, tries to not get caught by the enemy, makes it to the other side, and the other general reads the message. Okay? It's the only way they can communicate. So they can send messages through messengers. But, of course, the messengers might be killed. You know, messenger is kind of a dangerous job. It's not one of the best jobs when you're a soldier. They can be killed on the way. So the messengers can be killed. So how do you solve this? Two generals. So what do you think? How do you solve it? Well, let's try something simple. G1 sends the time that he wants to attack to the other general in message. Okay, fine. Okay, fine. But G1 is not sure that G2 actually got that message. So if G1 actually attacks, G1 is not sure that G2 is going to attack at the same time. So how does G1 be sure that, how can he be sure that G2 got the message? Well, maybe G2 just sends an acknowledgement, okay? He says, another messenger back saying, yes, yes, I got the message. Everything's fine. Okay? So that's it, right? Solved or not? What can happen now? Well,
G2 doesn't know.
Yeah, the messenger with the acknowledgement maybe doesn't arrive, so G2 does not get that acknowledgement. So how can G1, how can G2 be sure that G1 got the message? Well, send another messenger the other way, right? Well, it seems like it's not so simple. In fact, you can prove that if the messenger travel time is unknown, I mean it's not bounded, it's unknown, you don't know how long they're going to take, you can actually prove that there is no solution in this case. This problem is impossible to solve. So some distributed problems cannot be solved. Some things are impossible. So not everything that we do, we can make it work. Some things that maybe seem not so difficult are actually impossible. Okay? Okay, now let's apply this to distributed systems. Okay? Two nodes, generals are like nodes. They need to agree. Maybe I have a database, a bank has a database with 2 copies, and it contains the amount of money in my account. So they probably should agree on the same value, okay? So they need to agree. But they communicate by messages on an unreliable channel. The messages can drop. Well, in that problem, if you don't know how long the message can take, so in the certain case where there's no bound on the message travel time, that is impossible to solve. Well, so what do we do? Agreement is hard, okay? It's a core problem. I mean, agreement is important. It's clear. If we have databases, information, I have to agree on the other. If I send something to somebody, I want to know they got it, and they want to know I got the reply, and so on. Huh? So that's a core problem. So this problem is called consensus. So this is one of the core problems of distributed systems. So it's maybe even the most important core problem. And how do we formulate it? So it's like this. All nodes propose some value. They say, I think there's 100 euros in his account. The other guy says, and he did these transactions. Oh no, it's 110, and he did another set of transactions. So they all propose a value, but some nodes might crash at any time. Okay? Despite that, despite the crashing, and crash can happen at any time in this algorithm, despite the crash, all nodes must decide on a value eventually. That means after finite time, they must decide on the same value, okay? And only decide on values which they proposed. I mean, it's very easy, right? All the nodes just say the result is 0. But nobody proposed 0. That's not good, huh? Oh, or they all eventually decide, but on different values. It's not good either, huh? Okay? But they decide the same value, but it's not a proposed value. You see, these 3 conditions you can get any two of them is very easy, okay? Any two of these three is very simple. You can eventually decide and decide the same, but if it's not any proposed value, then it's not useful, okay? You need all three conditions. And that's why it's hard. Any two of these, you can do it easily. But I got you into a corner, okay? I want all three. Shit, it's much harder when you want all three, okay? It's a hard algorithm to do. And so the first people who did these algorithms, that was a major achievement. So the most famous algorithm in distributed computing is a consensus algorithm called Paxos, around 1990, invented by Leslie Lamport. And it was a major thing. People did not know how to do before, okay? So of course, consensus, I mentioned already, databases, you can see it's important that nodes agree, So for example, databases. This is something that happens all the time. Whenever you buy something, whenever you take money out of your bank account, the information is stored in a database. And in order to be reliable, it has multiple copies. And it's even worse than that. The copies are not in the same building, because if there's a fire, then it will destroy both. So the rule is they have to be far apart. So a bank, like Belfius or KBC or whatever, any bank, Paribas, they have databases that are physically widely separated by kilometers. So if one of them goes down because of a bomb attack or because of a fire, they know the other one will still work, okay? Or because electricity goes down in one. So they cannot even be in the same building. So you see, they must be separated. It's crucial. But they still have to agree, of course. So we got ourselves in a corner here, Okay? So databases, they work on the modifications of databases is by a thing called a transaction. And a transaction is an atomic operation, which means that it's all or none. You either have the before state or the after, no intermediate states. So if the database crashes, you will never see an intermediate state. Either it will be done or not done, but nothing in between. So if you have a transaction algorithm that's distributed, it has to do something called atomic commit. So either all the copies agree that the database commits, or they all agree that it aborts. Okay, so there's only two possibilities for the proposed values, commit or abort. Okay? You see, so that's one core problem. You see it's very important, and I haven't shown you yet how to do it, I show you a case where it's impossible. Well, that's kind of not nice, huh? If it's impossible, why am I even teaching a course if it's impossible? Maybe sometimes it's possible. So here's another core problem called broadcast. So broadcast is when you want to send information from one node to all the other nodes. Okay? And there's many different kinds of broadcast. So this one that I'm going to explain is called atomic broadcast. So it's a kind of very strong kind of broadcast. Okay? So a node broadcasts, okay, and then there's some conditions. If the sender is not crashing, so I'm saying not crashing, I'm saying he's correct. And when you say the node is correct, it means it doesn't crash. Then all nodes that don't crash, so all correct nodes, will deliver the message. The message will come there and go to the person sitting there, okay? And then there's another condition, because we're talking about atomic broadcast. That's what it means there's some conditions. So all nodes, all correct nodes deliver. They of course all deliver the same messages, not some random message that they invent, okay? And of course, they're all delivered, because it's atomic, they're delivered in the same order. So that means when I do an atomic broadcast, then all the nodes will get the message. But if somebody else does an atomic broadcast, so for example, if I have, let me make a picture, okay? It's good to make pictures. So here I have a bunch of nodes. So here's node N1. It's broadcasting a message M1, atomic broadcast. And here's node N2, broadcasting M2. And there's a bunch of other nodes. So in atomic broadcast, if this node does not crash, it will receive both M1 and M2, okay? So maybe M1 comes first and then M2. So the same order, it means that this node has to receive it in the same order. It cannot be like this. This is not allowed, okay? They have to be receiving it in the same order. All of the nodes. This one also has to receive M1 first, M2. So you see that's kind of a strong condition, huh? These two guys are sending messages at any random time, and they don't never talk to each other. Okay? And everywhere, including here and here, these two have to arrive in the same order. So that's kind of a strong kind of broadcast. Huh? You can see it. Huh? Okay? So that's another core problem. Okay? But let me now tell you something about this core problem. Atomic broadcast is actually exactly the same as consensus. That's weird. Right? They seem very different, right? Consensus, the nodes are agreeing. Here I'm broadcasting information with some atomic condition. Actually, the two algorithms are equivalent. What that means is that if I have a system, a library doing atomic broadcast, I can very simply do consensus. And in the other direction too. If I have a library doing consensus, I can in a very simple way, trivial, do atomic broadcast. So, for example, let me show you one direction. Let's say I have already, somebody has written an atomic broadcast. Well, with this one, I can actually make a system that does consensus very easily. How would you do that without reading the slides? Okay, I can do that. So the trick is that the message is arriving in the same order. Huh? You see, that's a very strong condition. Huh? So we're going to use that. Huh? So how does that work? I have a library. Somebody did already the hard work. He did the heavy lifting. He made this great atomic broadcast library. And I need consensus. Well, no problem. I can use that atomic broadcast library. So how does it work? Well, in consensus, each node proposes a value, right? We'll just let every node broadcast the proposal. And all the messages arrive in the same order. Remember? So the first one that's received will be the same one for all of the nodes. So just decide that this is the result of consensus. See, that's nice, huh? It's tricky, yeah? It's clever, right? We're using the atomicity condition, that the message arrive in the same order, to do consensus. So you can see that's actually a strong thing, huh? You might not think so at first glance, but the atomicity is strong. You could use it to make consensus, okay? So you just decide on the first one, and then the other ones that arrive, you just throw them away, okay? And then you have implemented consensus. You see that, huh? Because they have to arrive in the same order. So given atomic broadcast, I can do consensus. Okay? What about the other direction? Let's say somebody has worked very hard and did a consensus library. If I have that library, can I do atomic broadcast? How would I do that? Ooh, that seems harder, huh? It's a little bit harder. How would you do atomic broadcast? So I can force the nodes to agree. Well, but how do I do atomic broadcast? Well, what do the nodes have to agree on in atomic broadcast? What is the thing that they are agreeing on, in fact? That's what I have to work out. Huh? They have to agree on something. Because that's what consensus is giving me. Okay, I can force the nodes to agree. But in atomic broadcast, I'm just broadcasting messages. What are the nodes agreeing on? What do you think?
The order on which they receive the
Yes, very smart. The order, exactly. They are agreeing on the message arrival order. The order has to be the same. So how do you do it then? It's slightly harder. Each node proposes an order. M1, M2, M3. M1, M3, M2. Okay? They propose an order, they run consensus, and consensus decides what is the actual order. But that means if the message actually arrives in a different order on the node, it could on the network, you don't actually deliver it to the application until you do it in the right order, okay? So you have to distinguish the message arriving at a node, but when it arrives at a node, it comes into the broadcast algorithm. It doesn't go immediately to the application that you're using, huh? So it goes into the broadcast algorithm, the local piece of code, and when they have decided on the right order, then maybe it's too early. Maybe M2 has arrived, but the consensus says that M3 should go in first. Well then, you don't give the M2 immediately to the application. You wait until the M3 comes, then you give the M3, and then the M2. Huh? You see? So you have to be very careful how you think about these algorithms. Huh? So when a message arrives at a node, it does not immediately go to the application. It goes to the piece of the broadcast algorithm that's on that node. You see that? Huh? And then it can go up to the application when the broadcast algorithm decides that it should. Huh? See how it works? Okay, so that's a very important intuition, okay? You see it's a little bit harder the other direction. Because it's harder because the thing that they're agreeing on is actually a sequence. It's a little bit more than just one thing, huh? They're agreeing on a sequence, the order of a sequence. But that's fine. When they agree on any data structure. Huh? So of course it can be anything, including a sequence. Okay? So with this you prove that they're actually equivalent. So these two problems, which seemed to be very different, are actually not different at all. They're the same problem. Okay? So this is important, of course. Huh? It means if I write a library to do atomic broadcast, then I also have solved consensus. So this reduces the work. Huh? So we can factor out the algorithms to only do the pieces that you have to do. Huh? So this is one example of that, but we're going to see other examples in the course. Okay? Okay, now let me give you some more intuition. So you see, I'm giving you intuition here. Huh? So I'm making formal definition, but I'm also giving you some kind of feeling for it. Huh? Now remember I told you that the two generals problem was unsolvable. Well, let's look a little more carefully at that. Okay? Because there's different kinds of distributed system. It depends on how long the messages take. So there's one kind which is called an asynchronous system, where you don't know how long the messages are going to take. In fact, it's unbounded. It means you send a message, it could take any finite time. It could take 1 millisecond, or 10 seconds, or 5 years. Sometimes you read an article about someone receiving a letter that was sent 50 years ago. So occasionally you have articles like that in the newspaper, huh? Because the post office notices that there's this letter sitting on the bottom of this big room, and they, we didn't deliver, let's deliver it, and it's 50 years later. It happens. So the postal mail is kind of asynchronous system, huh? Message sometimes, so usually they're very fast, but sometimes it can be very slow. Okay. So that's an asynchronous system. So the two general system is actually, and we defined it as an asynchronous system, okay? So this is actually the hardest kind of system, okay? Now, of course, there's a small problem, is that the internet is basically asynchronous, okay? There's no guaranteed time between the message going through IP or the IP protocol. This is the basic internet protocol. It's a best effort protocol. And you're not really sure. It tries to make it go fast. Usually it's fast, but no guarantees. And sometimes it's very slow. Okay? You can have congestion, for example. Or the router can go down and maybe it reroutes. Okay? So the design of the internet was not designed with any bounds on the messages. If you've taken a network course by my esteemed colleague Olivier Bonaventure, who's actually very famous because he actually makes internet protocols, you will know that. You will understand that IP, there's no timing. It's a best effort protocol. So the problem is that this internet is essentially asynchronous. Okay, this is kind of a problem. The problem is that you cannot solve consensus in an asynchronous system if even one node can crash. I mean, if nobody crashes, you're fine. But if even just one node crashes, minimum, just one out of many nodes, then you will not have an algorithm that always works. Sometimes it breaks. You cannot solve it. Okay? So that's kind of a pain, isn't it? Because if the internet is asynchronous, what do we do? Okay? You can see that people get worried when they get a result like this. Huh? So this is a famous result, actually. This is a famous result. It's so famous it has its own name, FLP result. There's a proof of this that we might see in the course. I mean, it takes a little while to explain it, because you're talking about all possible executions. But the result is very simple. And it's like the two generals problem. If you don't know how long messengers can take, then there's no way you can guarantee that generals will agree. But if the internet is really asynchronous, then we're kind of in a bind, okay? If this is the end of the story, then the course is finished, right? It's easy. Luckily, it's not the end of the story. But you can say, there was a famous story, there's a famous anecdote on that. There's a famous book, Snakes in Ireland. You know this thing? Chapter 1, there are no snakes, the end. Okay? There are no indigenous snake species in Ireland for some reason. Okay? So yeah, here it would be done. But if this is really true, this is true in this case, if this is going to stop us, it's over. We cannot do atomic broadcast, we cannot do distributed database, and other things which I didn't talk about, like leader election, where you also need consensus. So asynchronous systems are very nasty. But the problem is, they're the easiest to build. If you just build a system like internet, automatically it's going to be asynchronous. But somehow that's not good enough. You have to do something more. Okay, so asynchronous is the hardest. Okay, let me now give you some good news. There's another extreme, which is called synchronous system. Synchronous system is where you know exactly how long the messages are going to take and how long the computing is done. But let me focus on the messages. You know that all messages arrive in 10 millisecond guarantee. So that means if the message does not arrive in 10 milliseconds, you are absolutely sure that the message has been then failed, that has disappeared, that there was a failure. It's not true for asynchronous. If the message does not arrive in 10 milliseconds, maybe it arrives in 100 milliseconds, or 1 second, or 10 seconds. Who knows? You never can be sure that the message failed. But here, if the message exceeds that time, does not arrive, you know for sure, guaranteed, fails. So synchronous system is really nice, easy, okay, to program in. So local systems like LANs, local area networks, computers on Ethernet, for example, or clusters with a backplane, they are basically synchronous, okay? And Ethernet can have bounds, because it's a cable, and they're all connected to that cable, and you know how long things take on the cable, or on the cluster. So those systems are synchronous. And consensus is very easy in a synchronous system. You can solve it even if you have up to n-1 crashes. That's pretty good. Huh? You have a system with n nodes. Of course, one of the nodes has to survive, otherwise it doesn't really mean anything. But that's all you need. Only one has to survive, or more. Huh? And you can do consensus. That's great. So, of course, it's very easy. Let's just build synchronous systems, right? The problem is, synchronous systems are really, really, really hard and expensive to build. And especially if they're widely separated. You cannot really build them. It doesn't work. It goes against the laws of physics, okay? Physics, well, first of all, there's time of light, okay? If I have a system where the two farthest nodes are 1,000 kilometers, then how fast does light go? How much time does a message take between those two? Like 3 milliseconds, right? 300,000 kilometers per second. 3 milliseconds is a lot for a computer, huh? But that means the synchronous system, the bound is 3 milliseconds. But what if you have nodes that are close together? Well, you have to look at the farthest nodes. So the whole system has to run very, very slowly because it's very widely separated. So big systems, if you want to make them synchronous, they are very slow. I mean, LANs and clusters, which are synchronous, are usually pretty small. Huh? They're a few meters big, okay, or 10 meters. It's just a couple of nanoseconds, okay? But you cannot make fast synchronous systems that are big. Fast and big and synchronous, it's impossible, okay? So we cannot do this. It would be great if we could use synchronous, huh? Okay? So why is this actually? Why can you do consensus and synchronous systems? It's because you can detect when messages or nodes crash. Okay? So assume that every node sends a message to every other node. If I do not get a message from the node, okay, if I assume the messages are reliable, then I know for sure the node has crashed. Okay? That the node, I am guaranteed. Whereas an asynchronous system, I don't. It's totally different. You see, you have to, intuition is asynchronous and synchronous are really completely different kinds of systems. Okay? Okay. So what we do now, the internet cannot be synchronous, okay? If we wanted to make a synchronous internet, it would be really, really, really slow, okay? And the bigger it gets, the slower it would get, okay? And of course the Earth is a pretty big place, huh? And computers are pretty fast. Going around the Earth, what is 20,000 kilometers the other side. So that's already 1/15, that's already like 7 or 8 milliseconds. And if I come back, or no, wait, no, 70 milliseconds or something like that. Huh? It's really slow. And if I have a protocol that needs to do 1,000 messages, it has to like coordinate, like a database, 1,000 messages or something. Immediately it gets really, really, really slow, okay? When I even load a web page, people even complain now that it's slow. And the internet is not synchronous, okay? Because a simple web page has many, many, many things. And you have to, all those things have to come in for you to see it. So people love to build systems in layers. And the lower layers do many things. And you build even higher layers, and you're doing more things. But if it's all synchronous, it just gets slower and slower and slower, okay? So you cannot make a synchronous internet. So we're screwed, right? To say it in a polite way. So that's not useful for internet. So in fact, you can solve the problem by thinking a little bit more in a subtle way. You have asynchronous, so the internet, you can say it's like an asynchronous system, and clearly you cannot make it synchronous. But maybe there's something in the middle, okay? The internet, you could say that it's mostly synchronous. But what does that mean? That means if I have two computers on the same, that are close by, they're both in the university, then most of the time the messages are fast. And the most of the time there are bounds. I mean, if the routers are all working well, then it works fine. But sometimes the router goes down, or there's a cable breaking and it has to route another path, okay? And it's slow. So let's say 99% of the time the messages are 1 millisecond, and 1% of the time there's a problem with the router. Or even 1 out of a million even, there's a problem with the router and it takes 100 milliseconds instead of 1. So it's not really a bad kind of asynchronous system. It's actually an asynchronous system that is mostly synchronous. So the bounds are respected most of the time, and sometimes they're violated. Yeah, when you have failures, or when you have congestion. For example, if you have a lot of messages coming into the same router, the router gets overloaded and will drop some of the messages. Okay, that's called congestion, and that will cause delays if you want to send things. So the TCP will have to retransmit the packet, and the bounds will be higher. So, but that's rare. It happens only sometimes. So can we make this more precise? So it would be nice if we had a very precise model that was very close to the internet, that we build, and that is easy to write algorithms for. That would be best, huh? That means it would be as easy as synchronous, and it would be very precise, and the internet would be doing it, and it would still be kind of asynchronous, but the algorithms would be easy. So somehow this intuition, we have to make it precise. And you see that? So this was a big problem, huh? Now, when I'm explaining it to you now it's kind of been solved, huh? But 20 years ago, or 25 years ago, 30 years ago, this was a huge problem in the beginning of the internet, huh? People didn't really know what to do, how to write these algorithms. In fact, in the 1990s, so more than 20 years ago, distributed algorithms was a mess as a discipline. If I wanted to teach a course 25 years ago, it would be a mess. It would just be completely unorganized and weird. Whereas now I can actually teach you a nice course. Now people are kind of understanding it. Okay? So what is the solution to this? We need something that's kind of is closer to what the internet is, and that lets us write algorithms in a good way, not like asynchronous. So there's the concept, people define this concept of a partially synchronous system. So this is a precise mathematical thing. I'm going to give you the intuition today, but later in the course we'll see it. And you can say that the whole internet, all internet applications are built on top of this idea. Okay? Without this, there would be nothing. Luckily, people are clever and they invent the right concepts. So we're lucky that this actually works. Okay? This works actually. It's because of some physical laws that it works. Because the farther you communicate, the slower it gets. But if you stay close by, it's fast. So, and the exceptions, when it goes far, are very rare. So this concept was a really important advance in distributed systems. So what does it mean? I'll give you the intuition today, but we will see a formal definition of this. It's not very hard. It's a very simple definition, but it takes a while to feel what it is, okay? But it's very important because the whole internet and all the distributed applications are working efficiently because of this, okay? Because this idea fits very well the internet. Why does it fit well? Well, there's many reasons. It's partly because the internet is kind of hierarchical, because of laws of physics, whatever. Somehow nature is being nice to us and lets us define this, okay? And it works. So what is it? So a partially synchronous system is a system that when you start sending message, it starts out being asynchronous, and eventually it becomes synchronous. So what does that mean? It means there are bounds, but you don't know them. The bounds are unknown, and you will find them. So in a usual synchronous system, you know the bound. 10 millisecond, the message comes after 10 millisecond. If it doesn't come, you know the node is dead. But in a partially synchronous system, there are also bounds, but you don't know them. That seems to be kind of a small detail, right? Between that and asynchronous. Between that and synchronous. But the fact that you don't know the bounds changes everything. It means that the algorithm can start by assuming the bound is very small. And if the algorithm works, then fine. But if the actual bound is higher, if we're in one of these exceptional cases, the bound will be higher, fine. The algorithm will have to work longer in that case, okay? So the fact that the bound is not known eventually means after some finite time, eventually there's a bound, but we don't know in the beginning what it is. But there will be a bound, but we don't know it. But eventually there is one. That seems like a weird kind of thing. How does the knowledge of whether a bound exists or not change things? But actually it changes everything. It's very, very huge difference between this and asynchronous. Okay? Because in fact, maybe the bound is 99% of the time very small. So okay, fine. The algorithm is working. But the algorithm, because it's written for partially synchronous, it will also work in the case when the bounds are violent. Because that's, from the algorithm's point of view, it's just like the bounds are higher now, they're higher. But the algorithm didn't assume some value for the bound. It assumes that eventually it would know what the bound is, but it does not actually assume some number. Okay? So this is a very important thing. Okay? And in fact, if you look at consensus, this is like halfway. It's really interesting. In a partially synchronous system, you can solve consensus, so that's good. Not up to n-1, not as good as purely synchronous, but up to n over 2. Actually, just less than n over 2. So the halfway is like the break. If I have 10 nodes, 4 of them can crash in a partially synchronous system, and consensus will still work. So this was a major discovery, okay? This was the discovery of Leslie Lampo in 1990. This was the Paxos algorithm, which changed everything. In a partially synchronous system, you can solve consensus, and actually pretty good, n over 2 crashes. That means a lot of nodes can crash, and it still works, okay? So this algorithm is very practical, in fact. Whereas in asynchronous, you could do nothing. In a partially synchronous, which is maybe, seems to be only a small difference, you could actually do everything compared to that. See, it's a huge difference. And you can see how it goes from one to the other. In asynchronous, it's unsolvable, totally. In synchronous, it's solvable in the best case, up to n-1 crashes. Fine, best. But in this one, it's also solvable, but it's like halfway, n over 2. It's funny, huh? So this is a theoretical result. This has been proved, and this is, in some sense, a surprising kind of result. Nobody knew what it was going to be before they proved it. You see, so this is what makes the internet possible, actually. Okay? The fact that you can do this, somehow partially synchronous is a very nice kind of environment, much nicer than asynchronous. Okay? So, yeah, so the question, is this useful for internet? Yes, of course, Very useful. Many systems are doing this. So consensus algorithms are one of the motors of the internet, okay? They are one of the things really making all the software work, all the databases, and even things like agreement is more than just banking and databases, huh? Anytime you have information, any kind of information about anything, you make a blog or something, you want that and other people comment on your blog. So many people are adding comments to your blog. Well, you want everybody to see the comments in the right order, okay? You want the answer to question to come before the question, not the order to be switched, okay? So that's kind of like a consensus. They have to be agreeing. So consensus is like hugely important, huh? Already for banks and stuff, but not just for banks and things. Already that's still pretty big thing, but for many, many other things. So partially synchronous lets you solve it. So this is actually the major thing of this whole course, in fact. If you get good intuition on this by the end of the course, then I'll be very happy, okay? We're going to see lots of algorithms in this course, many, many things, and many of the algorithms will be for partially synchronous, so you're going to get a good intuition on that. But I'm already giving you the thing, huh? How do you say in French? J'ai déjà vendu la mèche, huh? So I already tell you what the trick is, huh? The trick is that the internet is partially synchronous. That is the foundation of everything, okay? You won't see that said in books, but I'm telling you that's the way it is, yeah? Oh yeah, sorry. It means that when you see a D on a slide, it means it's something where I can discuss with you. It means discussion. It means that I expect you to give me the answer, okay? So the course is a little bit interactive. Sometimes I'm going to ask you to tell me things, okay? So the question is this useful for internet? But I actually said it, unfortunately, before in this case. But so I expect you guys to do some of the thinking, you know? Okay, so we're almost at the end. Let me just say one more thing before we stop today. So you see already now that things are not easy, okay? The code is complicated. It's completely concurrent, huh? Have you ever written a concurrent program where you have 1,000 users that can type anything at any time, okay? Thousands. Facebook, you have millions of people interacting with it at all the times. YouTube, and they have to work, huh? So concurrency, hugely concurrent. Probably you don't have experience with that, huh? So you will get some of that intuition in this course, huh? After this course, you will be much more comfortable with concurrency, and even stronger with partial failure, okay? So these partially synchronous systems, they handle failure very well, okay? So partial failure. So basically, it's the opposite of what Leslie Lamport, his joke, huh? This was a joke he made a long time ago, huh? In the early days. If one computer crashes and it's sitting in Japan, your system doesn't work. That's completely weird, huh? It's terrible. That's how it was in the early days. Now, hopefully, it's not like that, huh? Even if in the Amazon database, 1,000 computers are crashing, you can still order something on Amazon, huh? Hopefully. But that's what they want, huh? That's how they make their money, huh? And usually it works. But let me just say one more thing. So the code is very complicated. So another thing we're going to learn in this course is how to write complicated code in a simple way. So you have to have some discipline. So it has nothing at all to do with object-oriented programming or anything like that, or UML diagrams. That's compared to distributed systems. UML diagrams is like child's playthings, okay? It's nothing compared to the complexity of this, okay? This is real complexity. You cannot solve it by making committee and inventing beautiful diagrams, okay? You can see I'm not a big fan of UML diagrams, huh? It doesn't solve very many problems. But here we have real complicated things, and there's no way to get around it, okay? So that's what we're going to see. And hopefully, and it works, and at the end of the course you'll have a good understanding. So that's the point, huh? And then you'll go out and you'll become billionaire on the internet or something. Huh? Yeah, why not? And then you'll think of your professor and give me some shares. I'm very happy, okay? That would be, for me, the perfect solution. So I will do my best to do my part of that, then you have to do your part. Right? So here, one more concept is the concept of failure detector. So this is like abstraction. You know, when you build programs, you need to build libraries that encapsulate things and so on. So failure is a big thing in a distributed system, okay? Detecting failure, sometimes it's hard. You have to, for example, do like heartbeats. You send message regularly and you wait until there's a return. So there's detecting different kinds of failures. What are the bounds? What is the round trip time? It's already can be complicated. So I don't want the failure to make my algorithms complicated. So everything regarding failure, I want to put it in a box, okay? So that the rest of the algorithm is simple. So this is a case when I want to really make my algorithm simple. So this was invented by another smart guy, who was Sam Tuig, also in the early 90s, but took years to figure out how to use it. The notion of a failure detector. So it's a piece of the system, a component, and inside, we don't really know, it can be very complicated, but it tells you what it thinks. It says, I suspect this node has failed, or I think this node has failed. So it's like an abstraction. It's telling you whether nodes have failed. So it's a very simple thing, huh? Failure detector, actually. It's a black box, and information is coming out, and it's telling you whether it thinks that nodes are failing or not failing, huh? It might say, I suspect a node, I think it's failed. And then later on it says, oh no, actually I was wrong, it didn't fail. But then later on it may again suspect. So sometimes it has to correct itself. Huh? So it's a kind of very special component. So this is a very simple idea. But if you use that idea, it makes the algorithms much, much simpler. So this is a question of abstraction, huh? Which is part of computer science and programming. The right abstraction makes the code simple, huh? So this is a case of that. If you have failure detectors, it makes the rest of the code really, really much simpler. Because all of the stuff about failures is inside that box, okay? And the rest of the algorithm can be actually a lot simpler. So we're going to see, I'm going to show you a lot of code in this course, lots of pseudocode, but even complicated algorithms, it will be one or two slides. So it will actually be very compact. The code will not be many pages. It'll just be, it'll be either one or two, and that's it. So very simple ideas, okay? So that's actually, this book was really, this was really the first book that was able to do that. So these two guys, Rashid Garoui and Luis Rodriguez, so I know both of these guys, they're very smart guys, okay? They're doing work on distributed systems. So they've figured it out, okay? How to make the code simple. So one of the ideas is failure detectors. Okay, so we're going to see that. Okay. There was a few more things I wanted to say today. I'll just take quickly. So also failures. Let's think a little bit about failures, okay? So we talked about synchronous, asynchronous, which is the timing things, okay? Let's say, what are failures? Well, the simplest kind of failures are crashes, where the system is running and it just stops running. Just all of a sudden it doesn't work anymore. That's called a crash stop, okay? But there are other kinds of failures. So let me present two of them. One of them, and there are two very funny ones. One of them is called Byzantine faults. This one is actually very important nowadays because it's used in cryptocurrency. And then the other one is called self-stabilizing. So this one is used in satellites and things in space, for example. So with Byzantine is the worst kind of failure. Okay? So the node is not just crashing, the node becomes evil. It tries to break the rest of the system. It fakes messages, it keeps track of all the information that arrives, and in a real smart way, as arbitrarily smart, it creates random messages, smart messages, to try to break the algorithm. Huh? If your algorithm is not made in a very special way, that Byzantine node is going to totally break it. Huh? If your algorithm is naive, the algorithm can pretend that it's transferring all your money to somebody else's money bank account. So if there's no protection against that, well, that's very bad, okay? So usually there is protection, of course, huh? In these critical cases. So a Byzantine fault is in the case when you are in an extremely hostile environment. You consider it to be like in a wartime situation. So most algorithms don't need it, but sometimes you absolutely need it. Like in a Bitcoin, where many people are doing transactions and it's money, it's real money. So I would be very happy if all that money came to me, okay? So the others would not be happy. So the algorithm is made so I cannot do that. So even if the nodes are evil, that doesn't work because it's based on cryptography. So Byzantine algorithms are actually extremely complex and heavy, and they use cryptography all over the place. It's explained in the book. So this is not a course on Byzantine. I'm just explaining this to you because it's an extreme case. Remember I told you that consensus can be done for 1/2 failures in partially synchronous. But failures, in those failures, are nice failures. They're nodes that just stop working. They're not becoming evil, okay? If the nodes become evil, I don't get half anymore. I can only go up to 1/3. So if there's less than 1/3 evil nodes, my Byzantine algorithm can still work. That means if you have an organization where a spy organization, and you have 1/3 are traitors, the organization can still work if you use the Byzantine approach, okay? Even if 1/3 are very smart traitors and are trying to break everything, they're working for whatever, some kind of specter or something, huh? They will not succeed if you're using a Byzantine algorithm. Of course, if there's more than 1/3, even one more guy than 1/3, I mean, it has to be less than 1/3. Huh? If it's 1/3 or more evil guys, then the Byzantine algorithm doesn't work. Okay, then not even a Byzantine algorithm can work. So that's the absolute best you can do. So for a consensus, for example, it only works up to for 1/3. Okay, and for many Byzantine, it seems to be 1/3 is the magic number. Okay, that's funny, isn't it, to see that? And these algorithms are important today with Bitcoin. So Bitcoin is a very strange thing, and this is not a course on Bitcoin, but somehow it captures people's attention and their money, and it's a solution looking for a problem, in my view. Okay, but it's so interesting that people keep hoping that there's a real problem it can solve, and maybe they find one someday. Okay, but in my view they haven't found it yet. Okay. So, but this is an example of Byzantine. Another kind of algorithm, weird algorithm, is self-stabilizing. This is a system that always can fix itself. No matter temporarily, it has a temporary crash. So in the previous algorithm, when a node becomes evil, it's evil forever. Okay, or a node crashed off forever. But here we're thinking about temporary. It means Julius Caesar is an example of this, because the poor guy, suffered from epilepsy. So every once in a while, his brain just goes quiet, goes crazy, and he thrashes around, and then he wakes up and he's normal again. Okay, somehow his brain fixed itself. So that's an example of self-stabilizing. It means temporarily, the system can be very weird, but eventually it fixes itself. Okay, that's actually possible. Okay, you can build systems that you can put them in any state. If I have a program with variables, you can assign any random values to these variables, and the system will be doing weird stuff, but eventually it will fix itself. That's amazing, kind of amazing, huh? So this kind of algorithm is also a kind of an extreme case. It handles any kind of temporary problem, okay? So we can do a little bit of theory. So such a system can either be in a reasonable state, this is Julius Caesar when he's normal, or in a legitimate state, this is when he's having his crisis of epilepsy. And then you have two properties that you need to prove. So convergence, if you're in an illegitimate state, that if you look at the future, it will always eventually go to a legitimate state, so it converges to the legitimate. And closure, if it's in a legitimate state, it will stay there. Okay? But of course, the system can sometimes then be perturbed. No? In a satellite, for example, cosmic ray can go into the computer, can upset the memory values, and so the system will go into a weird state, but it's able to fix itself. Okay? So this is a kind of failure that you can fix with this kind of algorithm, and this actually works. Okay? In some cases, in the cases where temporary failures are happening, so here's an example of a self-stabilizing algorithm. This is called the token ring algorithm. So I have a ring of nodes here. So each of these are computers. This was actually a competitor to Ethernet. It was IBM invented this. So there's a token going around, always. One token. And if you want to send a packet, you have to wait until the token comes. And when you have the token, then you have the right to send a packet. So if you do that, you're guaranteed that there will always only be one packet going in a nice way around the system, okay? Like that. But if you have a weird failure, maybe you have 2 tokens, or 0 tokens, or 1,000 tokens. Well, the algorithm is made that it will automatically fix itself. All those tokens will go away and only one will remain. It's kind of magic. And the code is actually quite simple for this. So this is actually a famous algorithm invented by a guy named Edgar Dijkstra in a 2-page little letter that he sent to the editor of Computer Science magazine. He invented this whole area of self-stabilization. So this was Leslie Leffert was very impressed by this. He said, it's so brilliant. But this is actually used, okay? So token ring algorithm, I think Ethernet probably won, but in the 80s and 90s, this was a big thing, the token ring algorithms. And they might still be used in some places. In the cases we have failures, right? So this algorithm will automatically fix itself. Another example of that is robots. Have you ever seen videos by these robots from Boston Dynamics, you know? These robots picking up things, and then you have some guy push the robot over, you know, poor robot falls. But the robot gets up and starts going again. So the robot is like self-stabilizing system, huh? Okay? Okay, let me go to the end now. Let me give some glimpse of the future. Okay? So the future, of course, is large scale. The future is everything is connected and things have to work. So we're going to see that in this course, huh? It'll be the second half. Systems are dynamic, and large-scale systems are almost always dynamic, of course, huh? Because there's no way you can, if you have 1 million nodes, there's always someone having a problem, huh? And there's many algorithms that do this. Well-known ones like Skype or BitTorrent, peer-to-peer, Gossip, Cloud. But now, a big thing now is edge computing. So actually, the cloud era, if you want now to look at my crystal ball, the cloud era is finished. You know, cloud was a big thing in the year 2000. What now is the big thing is edge. So the number of devices people have, it's not just mobile phone, it's your iWatch or Apple Watch or whatever, but it's also other things, sensors in your homes, Nest, everything. So this is growing exponentially, very fast. And it's already much bigger than cloud, okay? So this kind of system is extremely dynamic and has billions of devices. Okay, so let me end there for today. So distributed systems are everywhere. They're hard, of course. Many problems are used to a set of core problems. Internet, of course, is the main one. But there's a huge number of things built on top of that. Failure is important. And of course, this thing is still research, huh? What I'm telling you is a little bit still at the edge of research, huh? So I'm actually doing research in this area. So if you want to do a PhD in something related to this, then I can give you advice, okay? But you'll see that at the end of the course, maybe, yeah? So this is still kind of a research topic. I will tell you some of the solved problems, and you get some of the good intuitions, but there's still many things that people don't know in this area. Because of course internet is still a very young thing, huh? Internet is existing since 1970, 50 years, it's nothing. Look at all the other engineering things, building bridges or mechanics or Newton's laws. They've been around for centuries. Of course they have already a huge number of good solutions, but computing and the internet is a very new thing. So we're still actually inventing many of the solutions. Huh? So this is something I'm going to just touch you, tell you that it's not all finished, this area. Still many things going on. Okay, so let me stop here. Thank you all. Yes?
Just to know, is there a lab session tomorrow? Or?
No, no lab session. The labs, there's only two reasons we're going to do it. So this is not a course where there's a weekly lab, okay? So there will be that, the default, be no lab unless we tell you there's a lab.
Okay.
And there's two reasons why we're going to have a lab. One is preparing for the project. So there will be several lab sessions on Erlang and comparing and doing exercises, so you'll get all the you need. Also preparing for the midterm. I think people might be interested in that because they help you get very good points on the midterm. So we'll do a few lab sessions for that, okay? But otherwise there will be no other lab sessions. It's what used to be called the 30-15 course. It's a course with only half the number of labs compared to the lectures. It's a slightly lower volume than it's not a big